All right, this is just going to be a quick video that's kind of an introduction to integration. And the thing we want to announce here or declare here, which we will prove later on, is that the integral is actually the same thing as the antiderivative. And if you remember, we've already seen this symbol as representing the area underneath a curve, and that is in fact equal to the antiderivative. So that's something fascinating. We'll play with this idea a little bit more later on when we get into the fundamental theorem of calculus. But for now, we just have to understand that this notation is exactly the same as asking for the antiderivative. Notice in this notation, we call this the indefinite integral, and that's because when we saw this before, there was some a value, some b value, some upper and lower limits here, and that's not the case yet. Right now, all we're looking at is just this meaning that we're going to take the antiderivative. Pretty straightforward. And so along with that comes some properties that we need to know. So, for example, if we took the antiderivative of 0, well, remember the derivative of some constant is 0, so the antiderivative of 0 is just some constant. Or the antiderivative of a constant is always just going to be a constant times x, some constant k. This is going to become your coefficient times x plus c. So this k stays in the equation. It just simply becomes kx plus c. Or if you have a coefficient and you have some actual function, you can remove, like I said in the last video, you can just kind of remove this coefficient out in front and then take the antiderivative of just the function part. So you can just kind of not really ignore, but you can remove the coefficient to the front and then apply it later on after you've taken the antiderivative. You also can take antiderivatives if they're separate expressions added or subtracted together. You can separate them so that you have two antiderivatives or two integrals that you're going to evaluate. And these are some things that we kind of already went over, right? The antiderivative cosine is sine, and the antiderivative of sine is negative cosine. And this is just following that pattern of trig that we already know for the derivatives of sine and cosine. Now we just do the antiderivatives in the opposite direction. So it's really not that bad. All right, let's go ahead and go to the next page and practice some of these problems. So find the indefinite integral. Remember, this is just taking the antiderivative. So this is really pretty simple. We already kind of know how to do this. It's 2x, and now it was x to the 1, right? We could say that there was like kind of a little 1 there. So now this is 2x to the 2, and we're going to divide by 2. And because we're dividing by 2, again, because that's our new exponent, and then plus some constant. Well, if we clean this up, it ends up being simply x squared plus c, which again makes sense. Remember when we took the derivative of x squared plus some constant, it equaled 2x. So let's keep going with this. What would this be? Find the indefinite integral. Well, remember this is kind of like a variable, and so there's an imaginary coefficient, not really imaginary, but there's an invisible coefficient of 1 here. And so that's kind of like your k value on the previous page. And so this thing simply equals, again, you can think of it as a 1x to the 0 power, right? You could think that this is really what's going on there. And so this becomes just simply 1x plus c. That's all there is to it. Pretty straightforward, pretty simple. So whenever you see just the integral of just dx, and that's something to point out as well, the integral is always going to have a dx at the end in order to evaluate it. It has to have this kind of like bookend beginning and this bookend end to really work out the antiderivative there. So here's another one. I think you guys could try this one on your own. Give it a shot and then check back when you're ready. Make sure you pause the video. Okay, well this is x to the 1, so you just add 1 to the exponent, you get 2, and you divide by that new exponent. Not really much more we could simplify than this, so that's it. Let's go to the next page. Okay, a couple more here. I think you're getting the hang of this. I'm going to say that example 3 and 4 I'm pretty sure you could do on your own, so I'm going to let you guys go ahead and give those a try. Again, pause the video, and then I'll put the correct answers up there after you're done. Okay, well 5 would become 5x, plus some constant of course. 7x cubed would become 7x to the 4th, where we now divide by 4. So we have 7x to the 4th over 4 plus c. All right, let's do the last one together, because it's not that tricky, but I just want you to see how you can set this up. We can start off by saying, you know what, this is the same thing as the integral of 3x squared dx plus the integral of 2x dx. And we said that on the previous page that we could separate them like this. And this little trick is going to come in handy often when we get something complicated here that we need some help with. So now we can evaluate these two independently. And so the first one would become x to the, well, 3x to the third divided by 3. And we can see that these 3's cancel out. Plus the second one become 2x. This is an exponent of 1, and now it's going to become an exponent of 2, where we then divide by that new exponent of 2. And those cancel out. And so we end up that this whole thing simply equals, oh, I forgot something, right? Plus c. So we find out that this thing simply equals x cubed plus x squared plus some constant to c. Okay, that's it for the intro to indefinite integration. I'll see you guys on the next video.